So, as an example of a problem where you make use of Snell's law, we're going to solve one of my favorite problems. I kind of like this problem because it's an application of optics that doesn't really strike you as being about optics. But the idea is that at a certain time of day, the sunlight just barely starts to hit the bottom of the pool. If you know the width of the pool, how deep is the pool? Now, I typed this time into a sun calculator on the NOAA website, and it told me that at that time of day, the sun is roughly 22.5 degrees above the horizon. So I've sketched out my visualization that has all of the relevant information on it. And then the first step in my plan is to write down all of the pieces of information that I know. This theta 1 here is actually 90 minus 22.5 degrees because remember we want to measure the angle with respect to the normal. For my assumptions, I'm going to use the ray model of light. We don't need to use any of the wave behavior at this point in time. We haven't learned any yet either. We're also going to treat the sun as a point source. We don't want to take into account the fact that the sun actually has a finite size in terms of where the rays are coming from, so we're just going to treat it as a single point in the sky right at the center. Really, the only equations that I need to use that are terribly relevant would be Snell's law. And so to go ahead and solve for that depth, the first thing I need to do is solve Snell's law for the angle of refraction, which just comes from rearranging this equation right here. And then to find the depth, I'm using the fact that tangent of theta 1 is equal to the opposite side over the hypotenuse, opposite over adjacent. In this case, the opposite side of the triangle is the 4-meter width. The adjacent side is the depth that I'm looking for. And so right here now I have an equation that I can plug my numbers into to get a result. All I need to do is take and plug this in for theta 2. So plugging the numbers in, I go ahead, I get a result of 4.14 meters. Now, one of the reasons I want to point out why it's so important that you actually evaluate your result and don't just go ahead and take it for granted. When I first did this calculation, I actually switched these two numbers around. I switched the 1.0 and the 1.33 around, and it gave me an answer that wasn't reasonable. Had I not stopped to think about it, I would have gotten the problem wrong. But because I had an expectation of what the result should be, I knew that it needed to be somewhere in the range of the depth of a real pool, somewhere between, say, 3 to 12 feet. By recognizing that my answer was wrong, I was able to go back and figure out where my mistake was. So, like I said, I expect the pool depth to be between 3 to 12 feet. That's roughly 1 to 4 meters. This answer is slightly on the high side for what I would expect for a pool, but I've gone back and checked my work, and I'm pretty confident that I got things right. So the idea with the evaluate is just kind of a double check. Does it make sense to you? If so, explain why.